All right, we're back recording. We're about the last 15 or so minutes of class. All right, so you guys did a really good job on that Geneva Drive project. All right, but I want to get you guys kick-started on this rotational dynamics. Right. So the first few slides here, you have seen in the past because we did do a little bit of rotational kinematic motion with turntables last semester. Right. Like this slide you guys seen before. But you guys see these bottom four lines here: rotate, moment of inertia, rotational inertia, torque, angular momentum, and angular impulse. So before I said, well, we're going to save those for later. So now it's going to start coming up this week. So you guys seen the top half of this before. Like these top three rows are rotational kinematic motion, right? Like turntable. These two yellow lines are like centripetal force. It's a little bit different unit, right? But these bottom four lines, this is going to be new territory we're about to be going into right here. Right? Right. Right, was right. All right. Kind of same thing here. You guys seen the top half of this, but not quite the bottom half yet. All right. So when you guys see this Greek letter tau, right? It's going to stand for torque. This is like opening a door, turning a wrench. You'll have some radial arm R and some F force that you apply, right? Like I think I've said this before, but like why is the door knob opposite of the hinges? Right? Why not put the doorknob like in the middle or close to the hinges? Because if the doorknob was close to the hinges, would it be really, really hard to open the door? Right? You could apply like a really large force and it'd be really hard to open the door, right? But with the doorknob opposite the hinges, even with a small force, it'd be kind of easy to open the door. Why? Because this arc here, you're getting a large radial arm, like the full radial width of the door that it's pivoting about. Okay. Now, if there's a torque, this is a vector value. This is sort of analogous to force in a linear sense, but now it's a rotational sense. So it can cause an angular acceleration. Oh, that's this alpha that you guys have seen like a few months ago. You guys are like if there's a turntable speeding up spinning or slowing down spinning, there could be some angular acceleration in radians per second squared. Okay? Now this I is rotational inertia. It's like inertia, but in a rotational sense, which I'll show you guys here in a few minutes too. Okay. So you guys, on the left side is linear motion. On the right side in green is the rotational sort of equivalent, like analog. Right? Hey, look, this is Newton's second law of motion. F equals ma. Sort of the rotational equivalent of that is torque results in I times alpha. Okay, and it comes from R cross F. Right? The cross product means you need like a perpendicular component. Okay. A little trickier one that we're not probably going to get to for a few days is the momentum version. Right? So you guys remember momentum is just mass times velocity. Well, if the rotational equivalent of mass is like its rotational inertia I, and the rotational equivalent of velocity is this angular velocity, then there's something called angular momentum, which is going to be capital L, right, which is also a vector. Right? The torque is a vector, angular momentum is a vector. Right? And that'll be conserved sort of in collisions too, or there's a classic ice skater version of this that we're going to look at. So look for an ice skater. Right? And then this bottom one is kinetic energy. Now, this K kinetic energy, I might call translational kinetic energy. This one on the right, I might call rotational kinetic energy. But they're both energy and they're both in joules. Right? And oh, look at this, 1/2 mv squared versus 1/2 I omega squared. You guys see how you can just pop in the analogous parts and make equivalent lookup formulas, right? Which I haven't even fully explained exactly what a lot of these are, but that's okay. We're one thing at a time here. All right, this one, you guys remember it's going to come back. Right, so just you guys saw this yesterday too. Yesterday each day. Right, so turntables, don't forget that. All this kinematic stuff is going to come back. Some of your AP classroom questions involve some of these rotational kinematic questions. Right, turntable slows to top. Right, can you guys make these three graphs? Right, you guys saw all this last semester. This is all review. I put a little review on here because you guys saw all this last semester. Okay, right, it's all kinematic motion. Right, it's like displacement, velocity, acceleration, but now in a rotational sense. So that's all there. Okay. This one you guys did also see. This one's a little tricky, center mass, because every physics textbook puts this in a different chapter, so it kind of pops up a little bit all over the place. Okay? But it's just a weighted average. So if you had like a straight line, say I like have a big mass on the left and a relatively smaller mass on the right, okay? Suppose these were stuck to like if there's this low mass stick stuck through the middle. Where could I balance this on my finger? Probably pretty close to that black dot right there. How could I figure that out mathematically? You take a weighted average. So mass times location, you add all of those mass times location bits, divide by the sum of masses, that gives you sort of like an average location. Okay. Now this is true along one dimension. One of your textbook puzzles that I circled for you guys. Do you guys see number 11 that I circled? It has a piece of plywood shaped like an L. Right. You can just do that along each axis. Do that along the x-axis, then also do that along the y-axis, and it'll give you a Cartesian coordinate as the center mass. Okay. I also have an activity with foam boards that are like weird shapes where you can sort of do a version of those too. Okay? And there'll be an activity come up next week or two. Okay. All right, so just weighted average can be center mass. You guys sort of seen this before. You see it again. It's can't come back. Okay. All right, I got a couple of bonus slides here. Right. What makes something stable or not stable? So here's sort of physics definition of what's unstable versus stable, and there's a neutral one in the middle. Okay. So you guys ever tried to balance a pencil like this? It's like nearly impossible, right? Or put a ball on top of a hill because any small displacement is just going to take off, like accelerate more in that direction. That would make something definitionally unstable. Right? If something is stable, say if there's a picture frame hanging on the wall, you bump it a little bit, it's going to go back into place, right? Or maybe some object on a desk. Okay? If it returns to its original position, then we'll call it stable. And then these ones in the middle are a neutral situation. Like if you roll this ball, then it's just the same predicament it was to start with, so it's called neutral. Okay, all right. I don't think that shows up in the AP exam, but in some of the other textbooks it does. So that's a little bonus there. Okay, here's another one beyond the scope of this class. This one's bonus, but this one's kind of fun. You guys got a cell phone with you? You guys got a cell phone? I got a challenge for you guys. Right? You guys see the ones on the left? Like if you rotate it about this axis this way, it'll set up a stable rotation. Here I'm doing mine. Feel like scared. Here, let me flip over and show you guys this. Right. If I rotate my cell phone this way, like that's stable. It'll set up a stable rotation. Okay. If I rotate my phone this way, that's also a stable rotation. Okay. But you want to see something that's like extremely difficult to do. Okay. You guys ever try to rotate it this way? I can almost guarantee that you cannot do this. Can you flip it and makes a nice clean rotation like this? That almost never, ever, ever happens. Right? What will tend to happen is like it'll make this weird quarter rotation about. Right now, the reason for this is pretty complicated. If you guys know a YouTube channel called Veritasium, has a probably about as good an explanation as you can get, but it's like a whole like half-hour long video. So if you're curious about this, kind of a real-world application of this is you guys remember this O'Neill cylinder? Right? There's a reason they drew it with a really wide radius, but kind of short. Right? Your textbook version mentioned like it being kind of long like this, but that actually wouldn't be stable. It wouldn't actually rotate correctly. So that's like I said, beyond the scope of this class. But if that piques your curiosity, then go check that out. Right? Right. Anyway, let's get back to real basics though. Right? Okay, so now we're back to actually what does matter to this class. Right. So rotational inertia. I have two sticks here. I actually built this right here. It's rotational inertia sticks. Yeah, flip my camera over here. You guys can see this a little better. All right. All right. So I've got these 2-meter sticks with a couple of lab weights taped to them. Okay. Now this one here has them taped near the center. This one here has them taped near the ends. Okay. But it's the same lab weight. So if I close my eyes and I just lift them like this, they feel like the same weight. If I shake them like this, they feel like the same mass. That's all fine and good. Okay. If I launch them like javelins, they have the same motion through the air. Okay. But if I rotate them like this, then something really weird. You guys see the one in my left hand? It's really easy to change the state of motion in a rotational sense. This one in my right hand, it's really, really hard to change the state of motion, right? Even though they're the same mass, but somehow they have different rotational inertia. Because it's not just how much mass anymore. Now we're getting to how is that mass located. Right, I'm going to pass these around so you guys can do the same thing. Grab them each in the middle, shake them back and forth, and you'll feel a real significant difference. Right, you guys can feel that. Space. We got about 5 minutes left in class. If you guys can get those around, I suppose you can here. Okay. So, suppose here my animation example, I have the masses slide out like 3 times as far away. Okay. Here's the formula for this. It's the sum of mr squared. So it's mass times its location squared, and then the sigma means you add them all up. So if I have 2 masses, and I'm coordinator stick, maybe that's kind of small, okay? Then that could give you the rotational inertia. Okay, so I got mr squared here plus this mr squared gives me 2mr squared. On the right side, if it's 3 times as far away, and I square that, now that's 9mr squared. And then plus this one on the left side, 9 is, that's where I'm getting the 18. You guys see that? All right, 3 times far away, that's like a squared factor. So trying to speed it up or slow it down in a rotational sense is like 9 times more difficult if it's 3 times far away. You see that? Okay. All right. Now, there's like some classic rolly looking shapes that the math has been done. To prove this mathematically, you need calculus. And I'm not going to prove these, but I'll just show you the textbook version of these. Okay. So for a single point, it's just mr squared. Okay. Actually, for a ring rolling around the central axis, it's effectively a bunch of points that are just aggregated. It's the same thing. You guys see that? Because you can just add up all the individual points. And if you broke this into a billion points, it's just the same thing over and over. So it's still mr squared. Okay. Now, what about these other objects though? Like if you have a solid cylinder, isn't it true that some of the mass is distributed closer to the center? Like whatever this radius is, not all the mass is at that radial location. A lot of it's like closer to the center. So it's effectively not as much, right? And if you do the math, it works out to a factor of a half, right? Now, you do not have to memorize these. If AP wants you to apply these, then they'll give you this table or some version of this table, right? But you should understand the concept and be able to apply it if you have these values given to you. Right? A coin spinning on its edge like this works out like this, 1/4. Okay? If you have sticks rotating, well, if it's about the end, it looks like this. If it's about the center, it looks like this. All right, here's, whoops, I meant to, I thought I made some fixes. Sorry, I got bumped a little bit. The rolly ball is 2/5 mr squared, 2/5 mr squared, and a hollow sphere or spherical shell it works out to 2/3. Okay? So if you roll these all down an incline, they reach the bottom of the incline at different rates. Okay. That's one of the posts I got too. All right, are you guys okay so far? With like, all right, so trying to rotate something, right? It has different inertia depending on how the mass is distributed, like how much mass and how it's distributed. Okay, they give you I. Okay, all right. Parallel axis theorem. Okay, now guys, this one right here, AP. This has not been part of AP's book for the last few years, but they are starting to introduce this starting this year. So you guys are the first group of AP students for many years that gets this again. Okay? But this isn't too bad. This just says the rotational inertia is some initial rotational inertia plus, and then if it's rotating off axis. Like if I go back to this slide, do you guys see I have the axis defined as this dashed line for every single one of these? There's some dashed line that's actually rotating about. What if it's not rotating about that dashed line? For example, what if like you might be spinning this basketball on your finger? It'd be rotating right about the center. That's all fine and good for 2/3 mr squared. But what if it's rolling along the floor? That would actually be rolling along not through its own center, but like across the surface. That's a little bit different. That's actually more inertia. Okay? So all you do very simply is just say, well, I'll grab the number straight off the table, which was like 2/3 mr squared for basketball. Okay? And then say plus md squared for whatever distance to the axis is actually revolving around. Okay? Okay? So for example, if the ball is rolling across the floor, you say 2/3 mr squared straight off the table. Okay? You got md squared, but now this d is r because it's rolling on its own edge. It works out to a little bit more inertia than just straight off the table value. You guys see that too? All right. All right. All right. Torque. Okay. So you guys ever turn a nut with a wrench? Right. So the longer the handle, the easier it is to turn. We just talked about that with like opening a door, the more force you apply. Now, one more detail. This is a cross product. You guys see this angle theta right here? You really need a perpendicular components. Right? So R, F, sine theta. That'll result in a torque, particular tau. And that torque can cause an angular acceleration. Right? If there's a net torque, it'll cause an angular acceleration. How much angular acceleration? Well, it depends on that rotational inertia that we just talked about last few slides. Okay, you see it? I see what else I can fit here. Last couple of class. Now, AP just does clockwise, counterclockwise. A more strictly mathematical general version is called right-hand rule. I don't have time to explain this today, but maybe a couple of days. Right. I'll show you guys a better example of this in a couple of days, but this is a little bit involved for the last minute of class here. Right. This is a lab we're going to do. Here, I think this is a good one to end on. Equilibrium. Guys, if you're, say, in engineering school, you want to build a big static structure. What you're looking for engineering for static equilibrium is not only do the forces sum to zero along each axis, but also the torque has to sum to zero. And that's the full solution for building a static structure. All right, I got to end there because I'm out of time. But hey, you guys watch this AP class tomorrow. Classroom videos. Can you guys bring some earbuds? That's probably the best way to do it. You guys got some earbuds,
two, right?
Huh?
Video 1 and 2.
I think I put about 7 or 8 videos up there. Yeah, so I put a bunch of videos. They're all assigned. You should see them on your assignments. All right. You guys have a good day, good couple of days, and I'll see you probably on Thursday, I hope.
And they just